All right, so now I am going to move on to section 5.4, which is another test to to help us see if a series converges or diverges. These are called the comparison tests. And basically, for all of these, what it is I'm going to try and use a series that I already know to figure out stuff about one that I don't know. Okay. So, comparison test. The first part says suppose there exists some integer n such that an is less than or equal to bn for all n greater than n. Then, if the sum of bn converges, then so does an. So, if I'm wondering about an and I know something about bn, I can use that. Specifically here, I want a bn that is larger. If I find one that's larger that converges, then mine must also converge. On the flip side of that, if I find a BN that is smaller that diverges, then AN is also going to diverge. So let's practice that here. Example number one for each of the following here. Use the comparison test to determine whether the series converges or diverges. So the first one, 1a, is the sum from n equals 1 to infinity of 1 over n cubed plus 3n plus 1. So this one, my tests I know so far aren't going to help me here, right? Because if I try to do the integral of 1 over n cubed plus 3n plus 1, there's no way to. It doesn't work out, right? So instead, let's try to use a series that I know. Well, think about it like this. So our an, the one that I want to know about, is 1 over n cubed plus 3n plus 1. Okay. So let's think of there's one that I know about that kind of looks like this one does. Well, down here I have 1 over n to the third, right? So let's use 1 over n to the third. What I know about that is that this is a p series with p equal to 3, which means this sum converges. So if this one is larger than this one, I can stop and I'm done. Well, let's think about this. Down here, I have n cubed plus 3n plus 1. So I'm taking a term I already have here and I'm going to add more, which means the denominator is greater. So the fraction is smaller, like this. So I have found a larger one that converges, therefore this converges. Again, I have found a larger one that converges, so mine must also converge. Another example. Sum from n equals 1 to infinity of 1 over 2 to the n plus 1. Excuse me. Okay, so again, this one, there's nothing I can really do. And so let's think if I know one that I can use. Well, I know 1 over 2 to the n is geometric. What's being raised to a power is 1/2, because this is like saying 1/2 n, right? So this is geometric with r equal to 1/2. Remember, thinking back to section 5.2, I've got to see what the absolute value of r is. So that's the absolute value of 1/2, which is 1/2, which is less than 1, which means this converges. So if this is larger than the one I want to know about, then I'm good and I can stop. So think about it. I'm taking something from over here and I'm adding 1, which means the denominator of this one is going to be larger, which means the whole thing is smaller. So again, I have found a larger one that converges, therefore mine also converges. If any of that doesn't make sense, don't be afraid to let me know. Reach out. I will be happy to help you. Example 1c. sum from n equals 1 to infinity, 1 over the natural log of n. So this one's a little harder. There's nothing that's clearly like this one that I already know about, right? The ones I already know about are geometric, which is like r to the n. I don't have that. I don't have a power here. We also know p series. That's 1 over n to the p. Again, doesn't really look like that. And we also know the harmonic series, 1 over n. Doesn't really look like that. But can I use one of these here? This one has the fewest terms, right? Because right here I have n to the p. I don't have that. R to the n, I really don't have that. So let's just try to use 1 over n, because this is 1 over a thing. 1 over a thing. Let's see if that helps us out. So let's compare 1 over natural log of n to 1 over n. First things first is we know the diverges, right? It's the harmonic series, so it diverges very slowly, is what we said. So let's see how natural log of n compares to n. Well, I know that the natural log of e is 1 because this is log base e. E to what is e? Well, that's just 1. Natural log of e squared, my power is 2, so that's 2. Natural log of e cubed is 3, and on and on. So what I plugged in was an e, and I got a 1, which means e is my n, right? I plugged in e, and I got a 1, which means the natural log of n is smaller than n because 1 is less than e, 2 is less than e squared, 3 is less than e cubed, and on and on. So the natural log is smaller, which means the fraction is larger. So I have found a smaller one that diverges, therefore this one also diverges. So if any of that doesn't make sense, let me know. Moving on, we also have this thing called the limit comparison test. The limit comparison test. So again, I'm worrying about an. I want to know something about an, so I'm going to pick a bn that's kind of like it, okay? And what I'm going to do, the limit of an divided by bn. If it's equal to a number, then an and bn do the same thing. So if I know what bn does, I automatically know what an does. If I get it equal to 0, it only works if my bn converges, in which case an will do the same thing. If I do that and get it equal to 0, I've got to have a bn that diverges, in which case an does too. So for example 2, for each of the following, use the limit comparison test to determine whether the series converges or diverges. So we're going to worry about the sum for part A from n equals 1 to infinity of 1 over square root of n plus 1. So that's my an. That's what I'm going to use for an. So I want to pick a bn that's something I know that kind of looks how this one does, right? Well, I know the p series 1 over the square root of n, because that's like saying 1 over n to the 1/2, right? So it looks kind of like that one, and I know something about this one. This diverges because it is a p series where my power is 1/2. So let's see what happens to the limit as n goes to infinity of an over bn. So this is going to be the limit as n goes to infinity of an is 1 over the square root of n plus 1 divided by bn. It's like saying times square root of n over 1. So that's going to be the limit as n goes to infinity, In the numerator, I have square root of n. In the denominator, I have square root of n plus 1. Once again, I just want the largest term on top, which is the square root of n, divided by my largest term on the bottom, which is also square root of n. Those cancel out and give me 1. So since I got a number, an and bn are going to do the same thing. Since bn diverges, an also diverges. Like that. Example B. Sum from n equals 1 to infinity of 2 to the n plus 1 over 3 to the n. So once again, that is my an. So I want a bn that looks kind of like that. That's something I know about, right? Well, I have a 2 to the n on top and a 3 to the n on the bottom. So I can write that as 2 to the n over 3 to the n. And the reason I like this is because that's like saying 2 over 3 to the n. So this is geometric, with r being equal to 2/3, which means it converges. So that's helpful. I know that. This is one I know about, right? So I'm going to use it. So now let's do the limit again of an over bn. An is 2 to the n plus 1 over 3 to the n times, flip this one over and you get 3 to the n over 2 to the n. We'll look at what happens here. These cancel out. That's really nice. So then we just have the limit as n goes to infinity, 2 to the n plus 1 over 2 to the n. Largest term on top is 2 to the n. Largest term on the bottom is also 2 to the n. They cancel out and give me 1. So since I got a value, they are going to do the same thing. Since this one converges, so does this one. Converges. The last example we have for this, example 2c. Sum from n equals 1 to infinity of the natural log of n over n squared. So once again, that's my an. So let's try to think of a bn I can use. Well, I have something over n squared. So in your head, it would make sense then to let bn be equal 1 over n squared, which is a p series with p equals 2. So it converges. I know that, so let's try and use that. So the limit as n goes to infinity, an over bn. My an we said was the natural log of n over n squared times, flip the bn, we get n squared over 1. Well, that's nice because n squareds cancel out. Limit as n goes to infinity of the natural log of n. As n gets really big, that goes to infinity. So that's part C right here. But we have a problem. That only works if my bn diverges. We said this one converges. So that didn't work. It didn't help us. I've got to try something else for my bn because this one didn't help me. So, if 1 over n squared didn't help me, let's try 1 over n and see what happens there. Sometimes it's going to take you just trying things. Well, 1 over n is harmonic, which we know diverges. So maybe that'll work because that was our problem with the last one. So, limit n goes to infinity. An is natural log of n over n squared times, flip that, n over 1. That gives me, I can cancel out one of these n's, so that gives me limit as n goes to infinity of natural log of n over n. Well, as we have already said, n is larger than the natural log of n, which means the denominator is going to be really big, so this limit is equal to 0. But we have a problem because we said if that happens, Bn has to converge. This one does not. So it still doesn't work. So if 1 over n, if that didn't work, and then 1 over n squared, that didn't work, let's do what is between them and see if that'll work. So between 1 over n and 1 over n squared is 1 over n to the 3 halves. Let's try that. Because then this is a p series with p equals 3 halves, which means it converges because it's greater than a 1, right? So we're going to do the limit as n goes to infinity. An is natural log of n over n squared divided by my divided by bn, which is like saying times n to the 3 halves over 1. N to the 3 halves and then n squared. I can cancel out n to the 3 halves, which leaves me with n to the 1 half. Limit as n goes to infinity, natural log of n over n to the 1 half. As it stands right now, it's not really super clear which one's growing at a faster rate. So I can use a concept from Cal 1 called L'Hopital's rule. Take the derivative of the numerator. The derivative of the natural log of n is 1 over n. The derivative of n to the 1 half, bring the 1 half down. N to the power of minus 1 is n to the negative 1 half. Simplify this. A 1 over n on top means I can put n in the denominator. 1 half right here means I can put a 2 in the numerator. N to the negative 1 half down here means I can write it as n to the 1 half up here. N to the 1 half cancels out with n to give me n to the 1 half down there. So that's going to be the limit. N goes to infinity of 2 over n to the 1 half. As n gets really big, this whole thing gets really small, so 0 there. Let's see if that's good. 0 is what I got. Bn has to converge, which this one does, so I'm good. Converge, that means this one also converges. If any of that doesn't make sense, let me know.